Hi, everyone. My name is Kennedy Cole, and I'm the Outreach Coordinator for the Center for Urban and Regional Analysis at The Ohio State University. I'm excited to welcome you to our first webinar in the series From GIS to GeoAI, Bridging the Gap in Geospatial Education. This series is co-sponsored by Cura, the Library Research Commons, and OSU's Geography Department. Throughout this series, educators from across the country will talk about their experiences teaching GeoAI to the next generation of geospatial professionals and discuss what it means to be AI fluent in the context of geographic information science. Today, Dr. Yue Lin will introduce the three foundational pillars driving GeoAI's growth in the human geography area: data, algorithms, and computational infrastructure, and trace their evolution from early quantitative geography to today's machine learning and high-performance computing. Before we introduce UA, I want to mention a few logistical items. If you require closed captioning today, you'll find a box at the bottom of the screen labeled with CC. Click the box and select Show Subtitles. This will allow you to view subtitles during the presentation. During the webinar, feel free to submit questions at any time using the Q&A box. We'll ask as many of your questions as we can in the last portion of the presentation, and if we do not get to your question, apologies in advance. Chat has been disabled, so please use the Q&A if you have any questions or information to share with the organizers. As you may have seen on our website, this event is approved for one AICP CM credit. To claim your CM credits, log into your My APA account on the APA website and enter the event into your online CM event log. There will be a brief survey at the end of the event, and if you have time, we encourage you to provide your feedback to improve these events. If you have any additional information following this event, don't hesitate to email cura@osu.edu. To learn more about Cura's future events or sign up for our monthly newsletter, visit cura.osu.edu. You can learn more about the Research Commons at library.osu.edu/researchcommons and the Geography Department at geography.osu.edu. Now I'd like to turn things over to Harvey Miller, Director of the Center for Urban and Regional Analysis, who will introduce our speaker.
Okay, thank you very much, Kennedy, and welcome everyone to our kickoff webinar on the topic of from GIS to GeoAI. Very happy and proud to introduce Dr. Yue Lin. She is an assistant professor in the Department of Geography and Geographic Information Science at the University of Illinois at Urbana-Champaign. Her research examines how emerging geospatial technologies can be designed and used in ways that are ethical, socially responsible, and beneficial to humanity. More broadly, her interests span spatial data science, locational privacy, and the societal implications of algorithmic systems. Dr. Lin comes to us with absolutely impeccable credentials. She earned degrees at the finest geospatial science programs in the world. This includes a bachelor's degree in geographic information science from Wuhan University, a master's in geography from The Ohio State University, and a PhD in geography from The Ohio State University, OH.
I-O.
Thank you. Okay, so with that, Dr. Lin, please take over.
All right. Hi, everyone. Thanks so much, Harvey, for having me here and also introducing me. So today I'm going to talk about GeoAI and human geography, data, algorithms, and critical futures. And I want to think through with you what GeoAI means for geography, not just the technical capabilities, but also some of the critical questions we need to be asking as the field develops. So let me start by going back a little bit. This is a quote from Helen Kuklidis from 1986, and she wrote, "It is not often that geography is touched by a development having the potential to affect substantially all of the practical, technical, methodological, theoretical, and philosophical aspects of our work." She was talking about artificial intelligence and essentially saying that AI isn't just another tool. It has the potential to reshape everything about how we do geography. And I think we're seeing that playing out now in different ways that are both exciting and challenging. So in a 1992 article, OpenShell asked a series of questions about AI developments and applications at that time. The questions include, why do we need AI in geography? What kinds of geographic research are we doing with AI? What questions can AI help us answer better than traditional methods? What problems are we actually solving with AI? And are there any new theories being created in the process? So these questions are still very relevant today, maybe even more so, as GeoAI has become more prevalent in our field. So what does GeoAI look like today? Well, we're seeing it everywhere. For example, Google is developing their foundation models for population inference and trying to make use of that to understand population dynamics at scale. We also have these AI tools to generate synthetic satellite images of future flooding to help communities visualize and prepare for climate risks. And also, NASA released their spatial foundation models in orbit. So these are all incredible capabilities. And as we celebrate these advances, maybe we should also ask questions about what are the potential issues that come with all of these technologies. So AI isn't just powerful, it also comes with risks. For example, we are seeing issues with what is called the hallucinatory domain of generative AI, where models produce convincing but totally made up information. And we're learning about the massive environmental impacts of training these models, including the energy consumption and the water usage. And we're confronting the reality that this multi-billion-dollar industry is being built on this invisible and often exploited workforce of data labelers and content moderators. So yes, AI is powerful, but it is not magic, and is also not free from the human decisions and human consequences. So in this talk, I want to walk through, I'm calling the 3 pillars of GeoAI. These are the foundational technical components that make GeoAI possible, but they are also where many of the critical issues emerge. So the first pillar is data. Data is used to train GeoAI models and also being used for analysis. But beyond these technical roles, we also need to ask, for example, what are we collecting as data, and also what is being left out. So the second is models and algorithms, which are the methodologies through which data are being processed, analyzed, and interpreted. But we also need to ask, how do these systems learn? How do they make decisions? And also sometimes, how would they mislead us? And the third pillar is computing infrastructure. These are the hardware, software, and technological systems that support GeoAI. And we ask who has access to these resources and infrastructure, and at what cost. So again, these pillars don't just enable GeoAI, but also concentrate their risks. And through this talk, I want to invite us to think critically about what that means for geographers. So let's start with data. Data is the foundation of many things in GeoAI, is what the model learns from and also the subject of what we analyze. But again, before we get into a technical side, I want to step back a little bit and think about where geographic data comes from. So the quantitative revolution in geography brought a real shift in how we thought about data. In the US, the 1960 census was an important moment. For the first time, a combined population and housing questionnaire was mailed to all the urban residents nationwide. And these became a primary source for large-scale geospatial research. And today, the data landscape looks very different. We can now work with satellite imageries, large map collections, street view images, movement traces, sensor networks, and georeference tags. And the amount and heterogeneity of geospatial data have also increased substantially, which is important to make GeoAI possible. So when we say data in GeoAI, again, it actually plays 2 different roles. The first is as training input, and this is what the model learns from. So when we fine-tune a vision model, for example, on street view images, or when we pre-train a foundation model on satellite imagery, we are using data to teach the model what the world looks like. And the second role of data is the analysis input. And this is what we actually want the model to analyze. So we feed the model new mobility traces, new maps, and ask the model to make sense of them. So these two roles can easily blur together, but being able to distinguish them still matters because the biases and gaps in our training data will shape what the model can and cannot do with the new data. And this brings me to something that geographers have known for a long time, which is maps have always been political and data is not neutral. For example, Brian Hardy's work in the 1980s show how colonial cartography erased indigenous territories and render lands as empty and ownerless. And also, likewise, Mammonia make the same point that maps can deceive, omit, and distort. So these things are not new, but what is new is that when the biased data goes into AI training, these distortions can get amplified at scale and also embedded in the models that people treat as objective. So here are some more examples of the socio-spatial biases in geospatial data. For example, Wikipedia, which is one of the main text sources for training large language models, has contributions overwhelmingly concentrated in the global north. OpenStreetMap, which is another widely used source covering points of interest, building footprints, and street networks, has editing and tagging dominated by men. So these socio-spatial differences in the data production process can directly influence what the models learn. So here, take Street View images as an example. These are one of the fastest growing data sources for understanding urban environments. And research showed that women and men perceive the same street very differently through the Street View images, and particularly about safety. So when we train a model on Street View images to evaluate neighborhood safety, for example, who contributed that data really matters. And if the underlying data reflects a biased viewpoint, the model will inherit that bias. So one response to the data bias issue is, what if we just generate the missing data? Take Street View images as an example again. The geographic coverage of this kind of data is highly uneven, especially in rural areas, population sparse areas, and many parts of the global south. So there has been a growing body of research using generative AI to synthesize Street View images for places and features where the coverage is rare or absent. So this figure here shows one example where AI-generated Street View images are being produced from satellite data. And the goal here is to fill the gaps and to make AI applications more geographically inclusive. So synthetic data is a promising direction, but generating synthetic data for model training also raises its own issues, which brings me to the next slide. And the issue is known as model collapse. When we train a model on synthetic data over multiple generations, something concerning would happen. So the model will first start to lose the rare and edge case features, which are also those that are already underrepresented in the data space. And then after several generations of training the model, the outputs of the model will become increasingly generic and eventually nonsensical. So as you can see in this figure, from the real image on the left to the generations 1 to 5 on the right, you can see that the images here progressively lose the details and degrade. So synthetic data as a debiasing tool has its own ceiling. So to further illustrate this pattern of model collapse, so we can see here, roads and buildings hold up relatively well across the first few generations of model training, partly because they're larger and also dominant features in terms of pixel coverage. But even these features eventually degrade significantly. And the features that degrade first and fastest are the small and visually rare ones, such as bicycles, traffic signs, fences, and traffic lights. And we can see that by the third and second generation, the fidelity for these smaller features already dropped dramatically. And these are also the features that matter most for evaluating things like pedestrian safety and accessibility, which is an area that has attracted a lot of research attention using Street View images. So although we might expect synthetic data to help fill in the coverage gap for the small and rare features, but because these features are statistically marginal in the real data space, they still may not be able to benefit from the synthetic data as much as we would hope. Okay, so now let's move to the second pillar, which is models and algorithms. This is where the data are being processed, analyzed, and interpreted that leads to decisions. But it is also where some of the consequential assumptions are being built in. Again, geography has been thinking about models and algorithms for automation for a long time. For example, Jeremy Dobson wrote in 1983, envisioning that automation can exist in all forms of geography, scientific and humanistic, basic and applied. And in many ways, GeoAI is a realization of this line of thoughts, where models are being developed and trained to automate geographic analysis and to let the machines handle complexity at scales that humans often cannot. So how do we get here? So geography has a long tradition of computational methods, from spatial statistics and geostatistics through spatial optimization modeling like location allocation to simulation approaches like agent-based modeling. And we also have image processing algorithms for remote sensing data, statistical machine learning such as clustering, and more recently, deep learning. And then now we have foundation models like GPT and geospatial specific foundation models. So each of these is a step towards potentially greater level of automation and also increasing technical capabilities to handle more complex geographic problems. But something that doesn't change across this evolving technical landscape is that every model has an objective. And the model is designed to optimize for something. And these choice carries value judgments even when it looks purely technical. So in geography, we've known this for a long time. The classic distinction is between efficiency and equity, and it has been widely discussed in the spatial optimization and location allocation literature. So here, optimizing for efficiency means maximizing aggregated coverage, or in other words, to benefit the most people or places overall. And optimizing for equity means ensuring fair distribution of access and resources. We can see that these two objectives often point to different directions, and the choice between them reflects the values about whose needs matters. So in 1977, Morrow and Simons wrote about efficiency and equity in optimal location, and they describe an observation from hospital planning. So they found that hospital administrators and health economists tend to favor efficiency, which means fewer and larger hospitals cluster together in medical centers, but citizens, patients, and welfare workers press for equity, which means more and smaller units closer to the people who need them. So we can see that this is the same problem, but with different objectives, it can result in very different geographies. And this tension between efficiency and equity also extends to the design of GeoAI models. Here's an example in geodemographic clustering, which use machine learning to group neighborhoods by their characteristics. And k-means here is a standard approach for clustering, which optimizes for efficiency. Or in other words, k-means minimizes the overall cost calculated as the within cluster variance. But in clustering neighborhoods in Chicago, when we look at the results by race, we can see that the average cost through k-means is consistently higher for minority neighborhoods than for white neighborhoods. And this happens because the clusters, which are represented by their centroids, tend to get pulled towards the majority subgroups. So here we explore an alternative approach called socially fair geodemographic clustering, or SFGC, to incorporate equity directly into the objective. So instead of minimizing the overall variance, this approach balances the cost across different social groups. And the results here is meaningful. We can see that it leads to a reclassification of neighborhoods, particularly on the south side of Chicago, into clusters that better reflects their actual characteristics. Okay, so the same issue from prioritizing efficiency applies to generative AI and large language models. So optimizing for efficiency here means that the model is designed to learn what is the most frequent in the training data and tends to drop or smooth over everything else. So this is demonstrated as an homogenization effect, where the model converges towards a generic representation and loses the diversity that exists in reality. Here we have an example. So we ask both humans and GPT to map neighborhood boundaries in Chicago. So on the left, you can see that the crowdsourced human responses are overlapping, and they're also having some clear disagreements. But these disagreement actually reflects the real diversity in how people experience and perceive their neighborhoods, because different people draw different boundaries as the place is being experienced differently. But on the right side, this is the AI-generated boundaries, and you can see that the boundaries here are more uniform and also less variable. And it can be seen that the model tends to homogenize both the shape and the extent of the boundaries. And we also found that with more recent commercial generative AI models, the homogenization effect seems to get worse. So in this study, we ask both humans and two GPT models whether they think a specific city in Ohio is located in Central Ohio. So Central Ohio is a vague geographic concept that generally refers to the area surrounding Columbus, Ohio, but it does not have fixed administrative boundaries or any official definition. This kind of fuzzy and vague geographic concept is actually very common in how people think about space and place. So in our experiments, you can see that for both humans and the LLMs, there is a consistent pattern in their responses. So as distance from Columbus, Ohio increases, agreement that the city is in Central Ohio first rise and falls, and there is an indeterminacy zone in between where people are not so sure. But what's interesting is that for humans, even for cities that are really close to or really far away from Columbus, Ohio, they still show some meaningful variations as reflected by this non-zero conflict ratio here. So for example, there is a city called Bexley, and it is right next to Columbus. But if you ask people whether it is in Central Ohio, there are still some people who don't think of it as being Central Ohio. So this variation actually reflects the different levels of spatial knowledge among the people, and also the fact that place is experienced differently by different people. But if you look at the more recent GPT models, so in our case, it is the GPT 4.1 at the time of our writing. So that variation largely disappears. We can see that the city is very close to or very far away from Columbus, Ohio, shows very little disagreement as demonstrated by these near zero conflict ratios. And this is likely because the model is designed to prioritize consistency over time and then tends to converge to the dominant patterns in this training data. So here, diversity is likely not an objective for training, but as LLMs become more widely used to simulate human behaviors and responses, or as a source where people seek answers and explore new places, these can create a concerning feedback loop where the homogenized AI-generated outputs can gradually narrow how geographies are being known. Okay, so now let's move to the third pillar, which is computing infrastructure. This is perhaps the most invisible of the three, but without the hardware, the software, and the system to run these models, GeoAI will not be possible. So again, geography has a history in using computers to create maps and other products. So this image here is from the Harvard Laboratory for Computer Graphics, which developed the SciMap system in 1967, and it is one of the earliest computer mapping systems. At that time, computing was a shared and centralized resource, and people need to manually key punch the data onto cards, submit them to computing centers, and then wait hours or even days for the printout to come back. And access at that time was pretty limited, slow, and also institutional. So these kind of constraints actually shape what kind of geographic analysis was possible at that time. So the infrastructural constraint has changed dramatically. Today, GeoAI systems run on GPU clusters, cloud platforms, supercomputers, and so on. Training a large foundation models may now require thousands of GPUs running in parallel for weeks. And Microsoft and Esri also launched their own GeoAI platforms on Azure, which is a sign that this kind of infrastructure has become more and more commercially mainstream. And also cloud computing has also somehow democratized access to HPC. Researchers who don't have their own hardware can now rent computing powers to run their own models. And it's not just the HPC and the computing hardware. There's also an emerging geography to AI infrastructure. This map here shows the data center locations across the US as of November 2025. So these data centers are connected by transmission lines and fiber optic networks, and they are also the physical places where AI models are running. But as you can see from the map, even in the US, their distribution is very uneven. The data centers are mostly concentrated along the coast, near major metropolitan areas, and also tied to existing power grids. And at the global scale, this kind of unevenness is even more so. Only 32 nations, mostly in the Northern Hemisphere, have AI specialized data centers. So you can see that the US is 26, the EU has 28, China has 22, but most of the global South has none. So when we talked about who has access to GeoAI infrastructure, it is still very heavily concentrated in a small number of wealthy countries and regions. And for researchers in the global South, there is a pressing question of how they can participate in building and using GeoAI. And beyond access, there is also the question of environmental cost. Running AI at scale requires enormous amounts of water. For example, data centers use waters in two major ways. The first way is the direct use for cooling the servers, and also indirectly through the water consumed by power plants generating their electricity. And we can also see research showing that training a single large language models can consume hundreds of thousands of liters of water. So this is a cost that is largely invisible in how we talked about AI, but it is actually very close to what geographers care about because it is tied to specific watersheds, local water supplies, and regional climate conditions. And where a data center is located actually determines whose water gets used. And this is essentially a geographic question, and it may deserve some more attention from our field. And there's also the carbon cost. This figure here shows that the carbon emission across different AI tasks is also different. We can see that the general purpose models are orders of magnitude more carbon intensive than the task-specific systems. So the generative tasks like image generation sits at the very far right of the chart, but you can see that the simpler tasks like text classification sits at the left. So this may be connected to a growing discussion in the GeoAI community about large and general purpose models versus smaller and task-specific models. The current discussion about this is still mainly on performance and accuracy, but the environmental cost may be another dimension to consider, especially as the difference in their environmental cost is not marginal. And also, when we talked about environmental costs, we need to know that the environmental burden from AI infrastructure is also not evenly distributed. In a news story about what's happening in Arizona, we can see that as data centers expand to meet the AI demand, they are draining power grids in areas where many indigenous communities still live without reliable electricity. And likewise, in California, research showed that data centers are disproportionately cluster in communities that are already facing the highest level of pollution exposure. So this is a pattern of environmental injustice that geographers are well positioned to study and to challenge. So far, I've talked about data algorithms and computing infrastructure, as well as the issues coming with them. The question now is, what do we do? What do we do with it as geographers and educators? So there is actually, this is actually a question that many geographers are actively working through. So we can see that there are universities starting to require students to study the ethical dimensions of AI as part of general education. And there are also some publicly available toolkits for responsible AI. Within geography, there is an increasing number of sessions in AAGs and other conferences about AI in education, and we're beginning to explore how to integrate AI in geography and GIS courses in different ways. And so as for my own view, I think teaching AI or GeoAI should, of course, emphasize the computational components, but it should go beyond the tools and the codes, because the technical skills, although they do matter, but they're not enough given the known issues in the data, algorithms, and the infrastructure of AI, as I talked about today. And I think it's important to cultivate the habits in students in terms of asking more questions when they work with AI. So for example, where does this data come from? What places or people might be missing? What bias might be built into how the data was collected or labeled? What is the model design or prioritized for? And how would that influence the results? And also what kind of resources, either environmental and financial, what kind of resources are needed to run the models? So these are difficult questions, and sometimes even us as researchers don't have the exact answer. But I think starting with asking questions like this is a meaningful step. For geography students, these would help them to cultivate the critical engagement with AI and also prompt them to think more carefully about what AI can and cannot do, and also ways of developing and using AI responsibly. And hopefully the habits of critical inquiry also doesn't stop at GeoAI, and it can become a foundation for how the students can engage with any future technologies. Okay, thank you all for listening. And here's a chapter on pillars of GeoAI that I co-authored with Dr. Jungwon Kim from Virginia Tech. And here is a QR code that links to my website if you're interested in my other research. And I welcome any questions and discussion.
Hey, thank you, Dr. Lin, for a very interesting talk. Again, I like how this is grounded in theory and some of the fundamental principles of spatial analysis, which I think should be informing our approach to GeoAI. As Kennedy just put in the chat, don't forget that if you have questions, please put it in the Q&A, and we got plenty of times for questions. So I hope we'll have a really lively discussion. Yeah, so I want to start off with a few questions just to get our discussion started. I want to talk about, I like how you went back to people like Stan Openshaw and Helen Kuklalis, who really saw a lot of this coming and really saw how geographic principles and spatial knowledge kind of fits into the coming AI revolution. Traditionally, geography has always had this tension between law-seeking or nomothetic knowledge and ideographic or description seeking. We still see that going back and forth. One of the things I've heard about AI and all these computational approaches is that it allows us to be scientific with very rich descriptions. And yet some of the things you talked about, like training on synthetic data, just seems to be going back to the old, like general nomothetic models that don't reflect the geographic richness and diversity that we would expect from these new methods. So I'm just wondering how you think this all fits into that kind of tension in geography. Are we seeking laws? Are we seeking descriptions? Something in between? And how do we make sure that these tools actually work towards what we're trying to seek in terms of geographic knowledge? That's probably a very big question. Sorry, but you seem philosophical.
Yeah, thanks for the question. I think I do agree that there is a tension in GeoAI developments at this time to so one trend is to develop this really large and general purpose models for being used for a variety of tasks and in a variety of geographic contexts. And there is certainly a community that is trying to develop specific and smaller models for smaller tasks. So one thing that I'm thinking about right now, as an example of the general model, is the foundation models. So there are many entities or many groups that are interested in developing foundation models, like Google or NASA. So that interest is both from the commercial industry and also from the government agencies. So the goal of foundation models is, so one of the goal is to have a general purpose output. So sometimes people call it embeddings. So this is the kind of output that is targeted to be used for a variety of downstream tasks, such as, so if we have an embedding of the Earth, we can use it for crop mapping and for classifying land use for all kinds of purposes. And also as the model grows at this time, the goal is really to develop embeddings for the entire Earth, so not just for a specific small regions. So one of the examples I have here is that NASA is actually developing a geospatial foundation models in orbit, making use of all the data that it has been collected in the past. So it's definitely this kind of interest in the communities to develop this really large and general purpose law-seeking models. But one thing that I'm also my research is looking at right now is what these models cannot do. So what these embeddings, these new data cannot do. So for example, if we're looking at place and human experience or humans' relationship with place, then relying on these kind of model may not be a good idea, because if you think about what most of these models are being trained on, many of them are being trained on satellite images or Earth observation data. Maybe some of them also incorporate social demographic data like census data or maybe mobile phone data. So that's possible. So a lot of the data goes into training these models, but there are a lot of things embedded in the human and space relations that they are not being able to be captured by the data, and they're also not able to be reflected in any of the model outputs. So one case I'm looking at right now with my other collaborators is to look at one specific applications of the embeddings data, which is called similarity search. So for people who are familiar with the Google's embedding and other kinds of embedding data right now on Earth observations, so one case that people like to highlight is how these kind of embedding data can be used for searching for similar places on the Earth or on a data space. So in geography, we're interested in what similar means. So if similar means physically similar or just similar through the eye of a satellite, then the use of these embedding data may work. But in geography, when we talk about similar, I think it's more rich. So it's about, for example, the social and it's about social relations. It's about maybe governance, policies. There are so many things go into what we mean by similar and some other kinds of concepts. So if this is the things that we care about in our research, then I think it should be more careful when we try to use this more general purpose data to inform, to inform our research or our practice. But yeah, so that's my response.
Well, to continue with this, I actually am very interested in this issue of like law seeking versus description seeking in geography. You're talking about they're trying to develop a general purpose model that's going to fit everything everywhere. And you seem to indicate that part of the issue is some things just can't be recorded, that there's a data measure issue, a data capture issue. I'm wondering what this says about I mean, is a general purpose model for geography possible in principle? I mean, does the world operate like that, or is geography a more of a, I don't want to say task specific, which would be the mapping to AI, but is it a more place specific thing, or is it something in between? Where do you think AI is going to take us in
I
that
think
5,000-year-old debate in geography?
Well, I think in an ideal world, everything can be captured as data, but the reality is our world is political and the data production itself is political. So there are lots of kinds of knowledge, forms of knowledge that are just not receiving as much attention as other forms of knowledge and goes into the training sets of AI. So I think so in reality, considering that the data production itself is political and there are marginalized forms that are not being well represented in the data production and or just not receiving as much attention as other forms of data, then I think a general purpose AI model may not be a good way, like the best way of envisioning what AI should what the fields should look like in the future. Yeah.
Yeah, and you also you just touched upon this right now about this geography of AI, essentially, not GeoAI, but the geography of where AI is, where the data is coming from, what's measured, and also where the computation occurs. And you mentioned this big global north versus global south divide, and you also and also a coastal divide, continental divide you're showing on the screen right now. And then also thinking about in the future, AI may follow water, not just energy, but may follow water. So, what does that say about really the future of thinking geographically and thinking at a global scale when basically we're going to see this type of modeling and approaches to knowledge that's going to have stark geographic divides? I mean, I can also imagine in the future talking about politics where countries may put walls around their data in order to make their AI better than other countries, thinking in particular like China versus the United States. So I'm just wondering on your general observations on this geographic divide in AI and where you see it going in the future.
I think so. I want to bring up an excellent article published in the Annals. I think it's this year. So the author is Dr. Xiao Huang, and the title of the article is GeoAI is Broadening the Digital Divide. So I think that article really covers this issue very well in terms of not only the AI infrastructure, access to infrastructure, but also where data are being collected and where the models are being developed. So there are lots of discussions. I would say an emerging discussion in this area. I don't really have a thought about what the future would look like, but one thing that one thing that I think about AI is that so there is a reading that I read about AI, which I thought is interesting, and the core idea is that AI itself is also not neutral and it favors centralization. So for example, if you think about the amount of data that needs to go into AI for training the models. So AI in its nature favors the centralization of data and also the resources, and like you said, the water and all kinds of things. So I think so beyond the digital divide, I'm more just curious about how do we sort of contrast um, or think of another way of developing AI. So fight against the concentralization nature of AI. So make it more democratized and not just through democratizing access through the cloud but just think about how to democratize, for example, who can contribute to the data and who can make use of resources to build models and to use models and in what way. So I think this is something that I'm very interested to look into. And I think also this is a very intriguing direction for me. But yeah.
Yeah, and just one last question before I turn it over to Kennedy, who will handle the audience questions. But you mentioned some of the ethical peer, principles of AI, and we certainly have to be concerned about the impact of data centers, the consumption of electricity, water, carbon into the atmosphere. So I'm wondering how do we? It seems to me that we would be less. We wouldn't need as many general purpose large language foundational models if we based our AI in theory. So what's the role as an educator? How do we get students to think in terms of how AI fills the gaps or advances theory as opposed to just running to these general purpose models to do our thinking for us, to put it bluntly? I mean, what's the role of that in geographic education to make sure students are ethical and also sophisticated consumers of GeoAI?
Yeah, I think so. One of my observations with my students is that they're pretty divided. So there's certainly one group of students who are enthusiastic of all the AI products, especially like large language models, like you said, the general purpose large models. They think AI can do everything for them. And they also think that, there are some free versions of the models. So they think, oh, so maybe we can use that for free and it will give us meaningful outputs. And I also have another group of students who are really anti-AI. They think AI is no good. There are issues everywhere, biases, hallucinations. So I think in geographic education, there's really a need to both sort of inform students to inform students what AI can and cannot do. So AI obviously cannot do everything, and also it comes at a cost. It's not free. It has environmental cost, at least, and some other cost. But AI is not full of bias, and it doesn't always give you made up information. You just need to develop the skills to identify those. So I think that's something really important that needs to go into the geographic education. And I think as if we're able to keep asking students these questions and sort of to prompt their critical inquiries in the use and development of AI, then they will have their own judgments in terms of whether we need, when we need these general purpose models and when we would need these specific task-specific models. So they would develop their own judgments, but some kind of critical literacy needs to go first. Yeah.
Excellent. Okay, thank you very much. Kennedy, we have questions from the audience. Go for it.
We do. Thank you so much, Dr. Lin, for the great presentation. I specifically really appreciated how much history you included. I found it really interesting. So we have a handful of questions. Apologies in advance if we don't get to all the questions. I'm sure Dr. Lin would be happy to take some questions after if you reach out to her or reach out to Kira. So someone asked, about representation in the data, there might be different takes from different perspectives. For example, if some groups in today's training data are underrepresented, why should they be represented? They may not really want to be in the training data, but also they are underrepresented for a reason. They don't have the digital footprint as other groups. So how can you boost the representations if they are simply not there in the data?
I think this is a wonderful question. And if you think about how a majority of the AI models are being developed right now, what goes in the training data? So at least for training LLMs, a lot of the data are somehow coming from the public web um, corpus, right? So uh, yeah, and there are, I would agree that there are a lot of the knowledge that doesn't get representation in that corpus. And also, if you think more broadly, a lot of forms of knowledge are not in written forms. So, for example, a lot of the indigenous knowledge, they're just not in written forms, and they're having their own alternative forms for communicating and to disseminating knowledge. So but the question is that so a lot of the groups, especially the underrepresented groups, they are not that they're not interested in using or being represented in the AI or in AI systems. It's just that they don't have access to contribute their knowledge and to have meaningful outputs from the systems, right? So I think it's really important to distinguish between these two kinds of scenarios and to really engage with the communities and to see how they react to the technology first and what they want out of it, whether they want their data, their knowledge being represented in this landscape, and if so, how. So these kind of critical conversations need to start before we assume that certain groups just don't have any interest in using these technologies. Yeah, thanks.
All right, thank you. Someone else asked, do you find that ethics courses are included in many GIS programs at colleges and universities? Or is there more work to do to ensure that ethics are considered in GIS curricula? Is it enough to teach students about evaluating GeoAI applications through traditional ethical frameworks?
Yeah, so for me, I'm teaching GeoAI courses, but mostly the technical side of GeoAI, like how to design a model and theories of models, things like that. But for me, I would so the way I teach ethics is that I would embed some questions in my labs. For example, there was a week I was talking about the 311 data, and I asked students to use the classification models we learned in that week to classify the 311 request. So I would have questions like, so instead of just asking students to develop models to analyze the data directly, I would also embed questions like, so if you map out the data, do you see any spatial patterns of the data? Do you think there's an underreporting areas of the data? So if you think about how 311 data is being collected, what's the issues in the data, things like that. So that would help them to, when they try to interpret end results that come out of the model, they would sort of embed that kind of thinking about issues of the data, and then that would somehow shape how they interpret the results. So that's some kind of small steps that I take when I'm teaching, like ethics or fairness, these kind of issues with AI. And I do think that there are increasing attentions about teaching the ethical dimensions of AI in curriculum, but and the ways there can be many ways. So, for example, it can be embedded in the existing courses, and it can be some small steps. So I think my example is like just a small steps of how I can embed some of the ethical trainings in my course. But there are certainly some opportunities to develop this a new course for GeoAI, or just like AI ethics or AI literacy in the curriculum, especially as students are making use of AI more and more, especially undergraduate students. And there's really a need to have a course and then to let them know what they can and what they cannot do with AI. But yeah, there are just different approaches to teach these things.
Yeah, and if you're more interested in this topic, we actually in August have Dr. Trislin Nelson from UC Santa Barbara, who is specifically going to be covering, GeoAI, including that in GIS curricula. So you should watch that one if you're free. So we have another question. Someone said, you mentioned how historical maps and geospatial data can reflect social, political, and technical biases over their time. So, what best practices or strategies might you suggest for not detecting but mitigating those biases in the process of digitizing and applying historical data for GeoAI? They also mentioned, I know some of you on this call have done work with Sanborns, which I expect to have higher accuracy, but I'm thinking ahead to work with other historical sources.
So yeah, so when I was working with Cura, we had this, but the project is ongoing. But I've been working on the Cura's project on Sanborn maps in the past as well. So yeah, so for Sanborn maps itself, it has biases. So you can not biases, but there are just geographic disparities in how it represents different kinds of geographic features, right? So for Sanborns, because it is an fire insurance maps, so not every geographic features in the world is being represented in this kind of maps. So you will find building footprints and like street intersections, things like that. So these are the kind of features that are interested to a fire insurance company. But so being able to recognize the purpose of maps is, I would say, is an important step towards recognizing what the map is telling you and what it is not. And when you're trying to use the maps to as training data to train and develop some models, what is being represented in the maps also, that kind of selection bias also goes into the models that you're training. So but again, I would say that being able to recognize the purpose of the maps is the very first step. And it actually, like you said, it embeds the kind of social and political biases of the time, or just how the map was created at the time. So.
Okay, great. I think we have time for just one more question, one quick question. And you kind of already covered this a little bit, but someone asked, since AI is trained using past data, what happens when novelty is encountered?
So yeah, so I think when novelty, so when the AI is so when the new data is somehow similar to the past data, of course you would see better performance. But when novel data goes into the training AI models, so there is a degradation that there is expected to have a degradation of performance. So one commonly encountered example is that if you see the self-driving cars on the street, so many of the data goes into training in the past. So maybe like in like 2020, at that time was taken from the daytime, right? So if you try to operate that car at night, then and you don't have the nighttime images, then it's just not safe, right? So the same kind of scenario applies to GeoAI. So some people try to mitigate that problem with synthetic data, but the problem with synthetic data is if you just don't have enough data points in a real data space for something, then if you're trying to generate synthetic to simulate that, probably is so in some cases it's still not gonna work, as good as you would expect. So that's always an issue, and I think that people are still figuring out ways to to address that problem.
All right, thank you so much. Well, thank you for your great insight for the Q&A portion. I'm going to pass it back to Professor Miller to close us out.
Yeah, thank you very much. And if I can add a comment to that, we train AI on the world as it is and the way it was in the past. But what if we want the world to be different? How is AI supposed to tell us that when it's only learning about how the world is? So,
Mm.
anyways, just a philosophical note to end. Thank you, Dr. Yue Lin. That was fantastic. Great launch, great beginning to our series on from GIS to GeoAI. Thank you. And our next webinar in the GIS to GeoAI series will be Friday, June 5th from 12 to 1 p.m. Eastern. Next month's talk is titled Geospatial plus AI plus Curriculum with Eric Shook, Associate Professor of Geography at the University of Minnesota. Eric works at the intersection of geography and computer science. He is the co-lead for education and workforce development for the NSF-supported iGuide project, and he's director of the GeoCommons and the Spatial Makerspace. So that'll be a great talk coming up on June 5th, 12 to 1 Eastern. All of our talks will be posted on Cura at our website, cura.osu.edu. And also we have a YouTube channel, OSU Cura. So if you want to see Dr. Lin's talk or any of our talks in the past, that's where you can go. So thank you very much. We hope to see you on June 5th. Thank you all for joining today and have a great weekend.